The film Gravity presented a vivid, terrifying vision. It showed us what surviving alone in space might entail. Astronauts faced a cascade of disasters. Their mission transformed into a desperate fight for life. The spectacle was stunning. Viewers were gripped by the sheer intensity of the struggle. Many wondered just how realistic these dramatic portrayals truly were. Space is indeed an unforgiving environment. The film tapped into our deepest fears about being lost and vulnerable in such an immense, indifferent expanse. It served as a stark reminder of the dangers inherent in venturing beyond Earth. One of the most striking early scenes involves an astronaut spinning uncontrollably. This uncontrolled rotation is a deeply disorienting experience. Imagine losing all sense of up or down. Your body is subjected to powerful, chaotic forces. Severe nausea and an inability to focus would swiftly follow. In the film, this uncontrolled spin is a direct consequence of a catastrophic event. It highlights the immediate physical challenges an astronaut might face. Finding a point of stability becomes the first critical task. Without it, any hope of recovery or reaching safety diminishes rapidly. This is not merely a visual effect, it is a genuine hazard. The catastrophic event triggering this chaos is a satellite debris explosion. This is often referred to as the Kessler Syndrome. It is a scenario where the density of objects in low Earth orbit is high enough that collisions between objects could cause a cascade. Each crash generates more space debris. This debris then increases the likelihood of further collisions. The film depicts this debris as a lethal cloud moving at incredible speeds. These tiny projectiles, traveling many times faster than a rifle bullet, can shred spacecraft. They can certainly pierce an astronaut's spacesuit with deadly efficiency. While the film dramatizes the speed and scale of such an event, the threat of orbital debris is very real. Space agencies around the world track thousands of pieces of debris. These range from defunct satellites to tiny fragments of paint. The International Space Station occasionally performs avoidance maneuvers. These move it out of the path of predicted debris conjunctions. So, while a gravity-style debris storm is an extreme scenario, the underlying danger is not fictional. Prevention and mitigation are constant concerns for space operations. The cosmos doesn't forgive carelessness with its orbital highways. Consider the horrifying prospect of a shattered helmet visor in space. This is a scenario many would dread. Your helmet is your personal spacecraft. It maintains a breathable atmosphere. It protects you from the vacuum. If that visor shatters, the consequences are immediate and catastrophic. The air in your suit would escape in seconds. You would lose consciousness very quickly due to hypoxia. The vacuum of space itself doesn't make you instantly explode, as some fiction suggests. However, the lack of pressure causes ebulism, where bodily fluids begin to vaporize. It is a grim and swift end. Then there is the profound isolation of being adrift in the dark. Imagine floating alone, untethered, in the blackness of space. Earth might be a beautiful distant marble below, yet it is unreachable. The stars offer no comfort, only a sense of infinite cold emptiness. This psychological toll would be immense. Hope could easily dwindle. Real astronauts on spacewalks or extravehicular activities, EVAs, are always tethered. They usually work in pairs. These safety protocols are paramount. Losing an astronaut to the void is a nightmare scenario that every space agency works diligently to prevent. In real-life EVAs, stringent safety measures are in place. Astronauts use multiple tethers to secure themselves to the spacecraft. The buddy system ensures that there is always someone to assist if problems arise. Spacesuits are robust, multi-layered garments designed to withstand micrometeoroid impacts and temperature extremes. A catastrophic helmet breach, while theoretically possible, is highly unlikely due to rigorous testing and design. The isolation, though, can still be felt. Astronauts speak of the awe-inspiring yet sometimes unsettling experience of being separated from Earth by only a thin layer of protection. Beyond the immediate threat of depressurization, space itself is hostile. The temperature in direct sunlight can soar to over 120 degrees Celsius. In shadow, it can plummet to minus 160 degrees Celsius. Spacesuits are designed to regulate temperature, but any failure would be critical. Then there is radiation. Without Earth's protective atmosphere and magnetic field, astronauts are exposed to higher levels of cosmic rays and solar radiation. This increases their lifetime cancer risk. Even with a fully functional suit, the environment outside is actively trying to harm you. Survival depends entirely on technology functioning perfectly. The International Space Station (ISS) often features as a sanctuary in space narratives. It orbits our planet at an altitude of roughly 400 kilometers. It travels at an astonishing speed of about 28,000 kilometers per hour. This means it circles the Earth approximately every 90 minutes. The ISS is a marvel of engineering and international cooperation. It serves as a laboratory, an observatory, and a base for space exploration. For astronauts working in its vicinity, it represents safety, supplies, and a link back to Earth. Its presence is a beacon of human ingenuity in the void. In a crisis situation such as the one depicted in Gravity, the ISS would be the primary target for a stranded astronaut. Reaching it would mean access to life support, communication, and potentially a ride home. In real space missions, the ISS is a vital hub. Astronauts live and work there for months at a time. It supports a wide range of scientific research. This research benefits life on Earth and helps us understand how to live and work in space for longer periods. Its significance cannot be overstated for current and future human spaceflight endeavors. It is our most substantial outpost beyond our homeworld. To prepare for the unique conditions of space, especially spacewalks, astronauts undergo extensive training. One of the most crucial forms of this preparation is neutral buoyancy training. This takes place in enormous underwater facilities, like NASA's Neutral Buoyancy Laboratory. Astronauts wear weighted suits in these giant swimming pools. This allows them to experience a sensation very similar to weightlessness. They can practice moving large objects. They rehearse complex tasks they will later perform in orbit. It is an essential tool for developing muscle memory for critical procedures. This underwater training is not just about physical acclimatization. It is also about problem solving and teamwork under demanding conditions. Astronauts run through emergency scenarios. They learn to communicate effectively while encumbered by their suits. They practice how to handle tool malfunctions or unexpected situations. This rigorous preparation builds competence and confidence. It ensures that when they face the genuine challenges of an EVA, their responses are as ingrained and efficient as possible. The goal is to make extraordinary tasks seem almost routine, minimizing the risk of error when the stakes are incredibly high. The dangers of space travel, as highlighted by films and real incidents, are not to be understated. Micrometeoroids and orbital debris, MMOD, pose a constant threat. These tiny particles, traveling at orbital velocities, can impact spacecraft and spacesuits with significant energy. While shielding can protect against smaller impacts, larger debris remains a concern. Radiation, as previously mentioned, is another insidious danger. Long-duration missions require careful monitoring and mitigation strategies to protect crew health. Equipment malfunction is also a persistent risk. Spacecraft are complex machines, and any system failure far from Earth can have severe consequences. History has taught us harsh lessons. The Apollo 1 fire, the Challenger disaster, and the Columbia tragedy serve as solemn reminders. These events underscore the inherent risks of pushing the boundaries of exploration. Even with meticulous planning and advanced technology, unforeseen problems can arise. Near misses also occur. The Apollo 13 mission is a famous example of ingenuity and courage turning a near catastrophe into a successful rescue. These real-world events inform safety protocols and drive continuous improvements in spacecraft design and operational procedures. We learn from both our triumphs and our failures. So, could someone survive the exact chain of events portrayed in Gravity? The film stretches the bounds of probability for dramatic effect. Surviving one catastrophic failure in space is difficult enough. Surviving multiple sequential disasters as depicted would require an extraordinary amount of luck, skill, and conveniently located resources. For instance, traveling vast distances between orbital assets like the Hubble, ISS, and a Chinese space station in a single EVA suit is not feasible. The orbital mechanics and fuel requirements simply don't align with that narrative. However, the spirit of survival and human resilience is very real. Astronauts are highly trained, resourceful individuals. The drive to explore and understand the cosmos is a powerful human trait. While films like Gravity take artistic liberties, they do tap into the genuine perils and the profound experience of being in space. Surviving such extreme scenarios as depicted remains largely in the realm of fiction. Yet the dedication to safety, the rigorous training, and the ingenuity of space explorers continually strive to make space travel safer. We accept calculated risks to reach for the stars.